This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Bocek, and today we will discuss 6 topics. The first topic is about the Bitcoin reserve. It's the following article here. The cryptocurrency world expected more when Donald Trump set up a strategic Bitcoin reserve for the USA. The implementation only includes digital currencies that were seized through legal proceedings, not direct purchases with tax money. And now 2 US states have moved forward with their own Bitcoin reserves. It's New Hampshire became the first state to approve a crypto reserve on May 6th, allowing their finance minister to invest up to 5% of the state fund in Bitcoin and precious metals. Arizona had a more complex path. The governor first rejected a Bitcoin reserve proposal, causing criticism, of course, from the crypto industry. However, a second attempt succeeded on May 7th, allowing the state to invest unclaimed assets like forgotten bank balances into Bitcoin and digital currencies. And more than 25 other proposals for setting up Bitcoin and crypto reserves in other states are still pending. Meanwhile, while several countries are considering Bitcoin reserve, like Brazil, Hong Kong, Russia, Sweden, Taiwan, and the Czech Republic, according to this article. Other governments like Great Britain and Poland have rejected Bitcoin reserves. El Salvador, once seen as a crypto pioneer, has scaled back its Bitcoin activities due to pressure from the International Monetary Fund. In Switzerland, the head of the Swiss National Bank opposed Bitcoin as a reserve, though the bank indirectly invests in Bitcoin via shares of MicroStrategy that is known for its substantial Bitcoin investments. And in my lecture, when I was talking about Bitcoin history, I am showing articles from 2011, also from this news site, 20 Minutes, and how the topics have changed is dramatically. What was once specialized financial use has now gone mainstream, showing that cryptocurrencies have become part of everyday economic discussions. The next article is about how tech companies respond differently to court orders for DNS blocking, and it's the following article here. Public DNS resolvers are being targeted in the fight against online piracy. Courts in France, Italy, and Belgium have ordered OpenDNS, Cloudflare, and Google to block access to pirate websites, but these companies have responded in different ways according to this article. OpenDNS took the most extreme approach by completely pulling out of countries where blocking orders were issued. In order to block over 100 sports piracy site in Belgium, OpenDNS simply announced it would no longer operate there, following the same strategy it used earlier in France. Cloudflare chose to comply with the orders while using what it calls alternate mechanisms. Users trying to access blocked domains through Cloudflare's DNS, the 1111, they will see a HTTP 451 error page that provides information about the blockage and links to the Lumen database for more details, like in this example here. This is here a court order from Belgium, and it involves the following site here. Now, Google's approach differs significantly. When users try to access blocked domains through Google's DNS resolver, it's the 8888, the system simply refuses the DNS query without any explanation. This leaves users seeing only a generic browser error with no information about why the site is unavailable. The Belgian court had actually ordered DNS providers to redirect users to a dedicated page explaining the block, which Google's approach doesn't follow. As blocking orders against DNS resolvers increase, transparency becomes more important for users to understand why certain websites can't be accessed. These blocking methods might eventually spread to other countries, including the US, where a new site blocking bill is proposed. Similar measures targeting public DNS resolver. And this Netflix and Disney-backed anti-piracy bill is called the New American Censorship System by the Electronic Frontier Foundation. The next article is about supply chain attacks. It's the following article here. A security incident has affected the NPM package rand user agent, which generates random user agent strings for web scraping and testing. Despite being deprecated, this package still averages around 45,000 downloads weekly. Researchers discovered that some versions contained malicious code not present in the project's GitHub repository, and the attack was detected on May 5th, 2025, when the security system flagged suspicious content in the newest release. The malicious code was cleverly hidden, only visible when scrolling horizontally in the source view on the NPM side. When activated, it creates a hidden directory in the user's home folder and establishes a connection to the attacker's command server. This remote access Trojan can perform various actions, including changing directories, uploading files, and executing shell commands. Simply downgrading to a legitimate version does not remove it. And the package developer explained that attackers obtained an outdated automation token from an employee that wasn't protected by two-factor authentication, and this allowed the publication of unauthorized versions that appeared legitimate to users. All malicious versions have now been removed from NPM, but affected users need to perform a system scan for signs of compromise. Security experts recommend using alternative, better maintained forks of the tools. Supply chain attacks are increasing, so make sure you containerize your dependencies during development to limit potential damage from compromised packages. The next article is on complex versus complicated systems. It's the following article here. Complex systems are fundamentally different from complicated ones. While complicated problems follow structured, repeatable solutions, complex problems are different. Complex systems often show 5 key characteristics that make them challenging to work with, according to this article. First, they display emergent behavior where the system's overall behavior can't be predicted by looking at individual components alone. Second, they exhibit delayed consequences where actions might only show their effect much later. Third, optimizing the part doesn't necessarily improve the whole system and might even make things worse. Fourth, past states continue to influence behavior even after the original cause is removed. And finally, small changes can produce disproportionately large and unpredictable effects. Several patterns here can help. Favor reversible decisions when possible, and think beyond immediate metrics to consider a holistic system health. Embrace innovation for unique solutions rather than relying on conventional approaches. Implementing controlled rollouts using feature flags, canary releases, progressive deployments, and shadow testing to minimize risk. Invest in observability to understand any state of your system without needing to ship new code. And use simulation to test changes by replacing past events or creating deterministic test environments. Consider also machine learning. This is very interesting when rule-based approaches reach their limits, as machine learning can adapt to emerging patterns. And finally, prioritize strong team collaboration, as complex systems rarely have a single right answer, making collective problem solving particularly valuable. Well, for me, complex and complicated systems go hand in hand, so I would not separate them. And I would not make this clear distinction here. And also do not confuse the classical O of whatever complexity with complex systems. The next article is from HA Proxy. It's about the state of SSL stacks. It's the following article here. It's very long, but very interesting. The SSL landscape has changed dramatically in recent years, creating performance problems and compatibility challenges across the internet. OpenSSL, once the reliable standard SSL library, underwent a major shift with version 3 in September 2021. While designed to improve security and modularity, OpenSSL 3 introduced significant performance losses in multi-threaded environments and removed APIs many projects relied on. The promised quick API support was abandoned, frustrating developers who had invested in this technology. Quick protocol, which integrates encryption at its core, faces adoption challenges because of OpenSSL's decision, according to this article. After rejecting community-developed solutions, OpenSSL recently introduced its own incompatible quick API, creating more fragmentation. And the transition created a dilemma for the entire ecosystem. OpenSSL 3 became the long-term support version, while support for the widely used 1.1.1 branch ended. Linux distributions had little choice but to adopt the new version despite its limitations. Testing reveals the harsh reality. In some multi-threaded configurations, OpenSSL 3 performs just 1% of the speed of competing libraries. This means companies might need to deploy 100 times more hardware just to maintain their existing traffic levels. And several alternatives exist with different trade-offs. There's Boring SSL, that's Google's fork from OpenSSL that implements quick but requires frequent updates. Then LibreSSL, a security focused with cleaner fork from OpenSSL but not widely packaged for Linux. Then WolfSSL, lightweight with excellent performance but requires extensive testing. And AWS LC, performance-oriented fork from Boring SSL, showing the best result when properly configured. And they did not consider Boring SSL or LibreSSL from the benchmarks due to the fast-pacing API changes in those libraries. And they also didn't consider Embed TLS and GNU TLS. They would require a rewrite of the HA proxy SSL code. And in performance testing, when they tested on 64 core machines, the difference were striking. WolfSSL reached 150,000 connections per second with linear scaling. AWS LC, with proper configuration, achieved over 180,000 connections per second. OpenSSL 1.1.1 managed 17,000 connections, and OpenSSL 3 managed only 1,500 connections per second. And the root cause is excessive locking and atomic operations in OpenSSL 3, where up to 96% of CPU cycles are wasted in lock management rather than useful work. And despite these issues being well documented for years, little progress has been made in fixing them. This situation forces organizations to choose between using unsupported older versions, deploying significant more hardware, or adopting alternative libraries that might lack the same level of distribution support. The last article is about migration from the distributed database CockroachDB to PostgreSQL for the reason that the customers, they do not require localized data. Here, as they state, none of our customers had required data localizations. So the feature that CockroachDB is having is not needed. So they switched back to Postgres. When they switched from CockroachDB to Postgres, they discovered major performance improvements and cost savings. What started as a mid-six-figure database bill in 2024, it dropped significantly, saving the company over $110,000 per year, despite provisioning a larger Postgres cluster than strictly necessary. The company originally chose CockroachDB, it was in 2022, for horizontal scaling capabilities, high availability, and SQL compatibility. They anticipated needing multi-region support for GDPR compliance. However, by 2024, those features were necessary as they remained in single region with straightforward transactional queries. And several problems pushed them towards the migration. Some queries ran faster on CockroachDB thanks to its optimizer. Most real-world queries were significantly slower. Testing showed many queries running 3 times faster on Postgres, with some up to 20 times faster. And the ORM generated complex SQL. Here in this example, they added and 1 equals 1 that interestingly caused to trigger a full table scan in CockroachDB, but not in Postgres. And while Postgres could apply database changes in seconds, CockroachDB would frequently time out during migrations. And this forced developers to manually run migrations one by one and create workarounds to avoid touching the database structure. And the production migration took just 15 minutes with 0 data loss, though they kept the maintenance window for 1 hour just to be safe. And after migration, they saw an immediate 33% drop in request latencies and quickly optimized more queries using the richer Postgres ecosystem tools. And a comment that I read online is also quite interesting. It reads here: from the point of view of an SQL engine in 2025, 100 million rows is a tiny table. They mentioned 100 million rows in their article. That was one of their biggest tables. And these days, this is considered small. So that's it from my side. See you next week.